All right, honors come. We are going to talk about intermolecular forces today. They are essentially forces of attraction between molecules. So we spent a lot of time during second quarter talking about the intramolecular bond. Intra means within. This is the bond that holds atoms together within a molecule. For instance, we talked about the covalent bonds that hold hydrogen atoms to oxygen in the water molecule. We spent a lot of time drawing the Lewis structures. We spent a lot of time also understanding the molecular shape of those Lewis structures, as well as the electronic shape of those Lewis structures, and how polarity came to be. Now today we're going to take polarity and see how it works with molecule to molecule, from one molecule to another. Okay? So these are all examples of the intramolecular bond, and we spent a lot of time studying this. Okay? But now we also spent some time talking about the ionic bond. Remember, the ionic bond was between a positive ion and a negative ion, and the electrostatic attraction that positives and negatives have where they attract each other, that holds sodium and chloride ions together, for example, in the compound sodium chloride. So here's a comparison of the intramolecular forces that we've talked about. We talked about the ionic bond where we had cations. Remember, cations are the positive ions and anions, the negative ions. And the electrostatic attraction holds things together. We talked about the covalent bond where we have electrons being shared between two nuclei. Okay? For example, in hydrogen. We also very, very casually brushed over metallic bonds. So in metallic bonds, we have the positive cations with the valence electrons that are free to roam about the positive cations in the metallic structure. And those roaming electrons are what causes metals to be able to conduct electricity and heat so well. For example, iron. Okay? So today we're going to talk about the bonds that hold water molecules together to form a liquid or a solid. We've got to have bonds between molecules for them to actually stick to each other enough to solidify or enough to make a liquid. These are called intermolecular bonds. Inter in Latin, this is an E, inter means between. So these are the bonds between molecules. Okay? So there are really four type of intermolecular forces. We're going to rank them in a bit. We're going to start off with the first one, dispersion forces. Okay? I want you to recall oxygen molecules. So if we look at oxygen is O2, right? So if I do the Lewis structure of oxygen, I have 12 valence electrons, six electrons for each oxygen. To satisfy the octet for oxygen, I have to put a double bond here. We know that oxygen molecules are nonpolar because those electrons are evenly distributed between the equally electronegative oxygen atoms. These electrons are all going to be shared evenly. We have the same electronegativity values. We're going to start looking at electronegativity values again for both oxygens. So these electrons are going to be even, no poles, okay? Under the right conditions, though, I can take oxygen and I can compress them or maybe even cool them enough to form a liquid. And if I have a liquid, that means the molecules have to stick together close enough that they liquefy. For oxygen to condense, there must be some force of attraction between those molecules to get them to stick together enough to liquefy. So what force is it? The force of attraction between oxygen molecules is called a dispersion force. Sometimes these are also called London dispersion forces, okay? Dispersion forces are weak, and they are the result of a temporary shift in the density of the electron cloud. So it's a temporary shift in the density of the electron cloud around that molecule, okay? Dispersion forces are sometimes called London dispersion forces after the German-American physicist who first described them, Fritz London. These are also sometimes called van der Waals forces, okay? So think about the oxygen molecule. These electrons that I've drawn in on this Lewis structure in reality are going back and forth between the nucleus and the electron cloud. They are the electron cloud, but they also have wave-like motion. On any given second, are they all going to be evenly distributed around the electron cloud of that molecule? Could I not, for a split second, have more molecules over on this side with this double bond than I do over on this side? Yeah, I definitely can. So for a split second, I could have more molecules over here. And that would cause this side of the molecule to be temporarily, partially negatively charged, which would induce this molecule also to have its electrons shift over to match that positive, because opposites attract. I will get some attraction going between the slight positive and the slight negative. Now, this attraction is just going to be temporary, because remember, the wave-like motion of the electron, it will eventually go back over here, and we will have that dipole disrupted, okay? So it is a very temporary thing. But if I get enough molecules and enough electrons happening, I'm going to have enough of these dipoles put together that will actually make enough forces of the molecules sticking together that I can actually liquefy or maybe even solidify some of these things that are even totally nonpolar, okay? So let's look at this. Dispersion forces, these London dispersion forces, exist between all particles. Anything that has an electron is going to have dispersion forces, okay? This is just talking about the electron cloud and how it is distributed across the molecule. Dispersion forces are weak for small molecules. So the smaller the molecule, the fewer the electrons. So the fewer electron clouds, therefore the fewer the dispersion forces, okay? And these forces have increasing effect as the number of electrons increases. Thus, dispersion forces come to become larger as the size of the particles increase. Because larger particles usually have more electrons. Larger, or we could also say stronger, as the size of the particles increase. For example, if I look at the halogens, okay, if I look at the halogens, we have fluorine, chlorine, bromine, iodine, and acetylene, okay? Fluorine, chlorine, bromine, iodine exist as diatomic molecules. These are part of our Brinkelhoff. Because the larger halogen molecules have more electrons, they have more dispersion forces at play, okay? There can be a greater difference between the positive and negative regions of their temporary dipoles, and thus stronger dispersion forces. This difference in dispersion forces explains why fluorine and chlorine are gases at room temperature, bromine is a liquid, and iodine is a solid at room temperature. So even though we have totally nonpolar things, the more electrons that are at play, the more dispersion forces we can have, and we can create liquids and solids with enough electrons. Okay, Next, dipole-dipole forces. We talked about polar molecules before. Remember, polar molecules are when we have an electronegativity difference that is greater than or equal to about 0.4 up to about 1.7. Okay? That will create a polar molecule. One atom will be a little bit more electronegative and therefore pull the electrons towards it. Polar molecules contain permanent dipoles. They are permanent. They are not temporary. They are permanent. That is, some regions of that polar molecule are always partially negative, and some regions of that molecule are always partially positive. These attractions between oppositely charged regions of polar molecules are called dipole-dipole forces. Okay, dipoles match up with dipoles, kind of like little magnets. Neighboring polar molecules orient themselves so that oppositely charged regions align. For example, if I have a whole bunch of hydrogen chloride, the hydrogen is less electronegative than chlorine. So let's review electronegativity really quick with our periodic table. So if you remember, electronegativity becomes much greater up in this upper right-hand corner. So if I wanted to put an arrow on the periodic table, electronegativity maxes out at fluorine, okay? Nitrogen, oxygen, fluorine, and chlorine are our most electronegative atoms on the periodic table. The further down to the left and down you go, the less electronegative we have, okay? Okay, and there are electronegativity tables in your workbook, and you can also look them up. All right, so let's go back to our notes. Hydrogen is less electronegative than chlorine, so we're going to have a dipole this way. Notice I've drawn in the positives and negatives. So if I have a neighboring hydrogen chlorine, I'm also going to have that same dipole. So the negative end of one hydrogen chloride is going to line up with the positive end of the other hydrogen chloride. And I can get a whole bunch of these in a row. And in fact, I can stack them. So if I put another hydrogen chloride at the top, I would have hydrogen on this end and chlorine on this end to line up as well. So we can get some pretty good patterns going with dipole to dipole when things are moving around. If they're still in the liquid state, they will move around, but they will orient as they move around according to the molecules that are around them as well, to go to the least energy state possible. Okay, so this kind of will give you a general idea of, in a liquid state, we don't have a complete, beautiful crystalline pattern, but we do have orientations that happen so that we have positives lining up with negatives. Okay? And these molecules will break these attachments and move around and then make attachments with the other molecules. It's a very fluid, pun intended, it's a very fluid arrangement. Okay, hydrogen bonding. Hydrogen bonding is a special case of dipole-dipole attraction. It's very special. We've got to have two things happening here. We've got to have a hydrogen, and that hydrogen has to be bonded either to nitrogen, oxygen, or fluorine. If that hydrogen is bound to something else, it is not a hydrogen bond. It is just a dipole bond. It has to be bound to nitrogen, oxygen, or fluorine. Okay? So for example, we could have hydrogen fluoride, water, ammonia, methanol. Okay? It's not a bond between hydrogen atoms. It's a bond that a hydrogen has to be bound to oxygen, nitrogen, or fluorine. Okay? So here's water. Water, H2O. Definitely, we've got our lone pairs here on the oxygen. We've got our hydrogens. Now, if I look at the electronegativity difference between oxygen and hydrogen, Hydrogen is 2.2 and oxygen is 3.5. So this gives me a difference of about 1.3, which is pretty dang high. The other thing that makes it a hydrogen bond so powerful is hydrogen and oxygen are both very, very small atoms. So they can fit in tiny spots. So we've got a very strong electronegativity difference in a very small area. So we will get oxygens from one molecule lining up with hydrogens of another, okay? And this orientation is very strong because of this very strong electronegativity difference. So we will get some fairly clear patterns with water. And this is why ice freezes in the crystalline shapes that make snowflakes. Notice we have this kind of hole between it. And this is why when ice freezes, it's less dense than water because we have this space here. We have this space generated by the crystalline structure. Okay? Hydrogen bonds also explain why water is liquid at room temperature, while compounds of comparable masses are gases. Okay? So, let's look at some molecules that have relatively comparable masses and look at their boiling point. So we have water, H2O. I'm going to just draw the Lewis structure here. We have methane. And we have ammonia. Okay, so water can definitely have hydrogen bonds, right? I've got oxygen here with hydrogen, and I can line up these oxygen molecules like this graphic above to create these hydrogen bonds that are very, very strong because this oxygen is so electronegative that it essentially pulls all these electrons to the oxygen. So this hydrogen almost becomes a proton, just a positive hydrogen out here. So we've got a very negative end here and we've got a very positive end out here, okay? So we have very, very strong hydrogen bond dipoles going on, okay? And notice that bent polarity makes that negative end very off by itself and the positive end pretty off by itself as well, okay? The electronegativity difference between hydrogen and carbon is just 0.3. And if we look at this, all these dipoles cancel out. I've got this perfect tetrahedral shape, so these dipoles cancel. So this is completely a nonpolar molecule, okay? And I really don't have much going on in terms of electronegativity there, okay? The next one is I have ammonia, okay? So when I look at ammonia, I have, once again, I have nitrogen bound to hydrogen, okay? So I can have a polar bond, but nitrogen has an electronegativity of 3.0 and hydrogen has an electronegativity of about 2.2. So that gives me a difference of about 0.8. So even though I can create that hydrogen bond, it's not nearly as strong. And this can create the hydrogen bond as well. This is not nearly as strong because the electronegativity difference here is about 0.8, and here it's about 0.13 or 1.3, okay? So even though that this is still technically a hydrogen bond, it's not as strong as oxygen to hydrogen. So notice methane, its boiling point is negative. Like it's going to be a gas long before we even get to room temperature. Room temperature is about 22 degrees Celsius, okay? So ammonia is also going to be a gas at room temperature, but notice it's like 130 degrees different, okay? And then water, because the hydrogen bonds are so strong because it's hydrogen with oxygen, the boiling point doesn't reach until we get to 100 Celsius, okay? So even though water is relatively the same mass as these, because of those super strong hydrogen bonds, it stays in the liquid state because it's so hard for those water molecules to break away to become a gas because of those hydrogen bonds, okay? So I want to go through and see if you can pick out which of the molecules listed below can form hydrogen bonds. Which of the molecules would have dispersion forces only, and which ones would have dipole-dipole. Okay, so take a minute, draw out the Lewis structures, look at what creates hydrogen bonds versus dipoles versus LDFs, London dispersion forces, and pick what intermolecular force is the primary force, because all of them have London dispersion forces. But which one's the primary force? Okay, take a minute. Okay, you ready to check? All right, let's look at hydrogen. Hydrogen is just this, totally nonpolar, right? So the only thing that we have for hydrogen is London dispersion forces. And it's not going to be very much because we only have 2 electrons at play. Okay, hydrogen sulfide, dihydrogen sulfide, or hydrosulfuric acid, depending on what state you're looking at, we're going to look like this. We're going to have this bent molecule, and yeah, we have some differences in electronegativities, but we don't have hydrogen bound to oxygen, nitrogen, or fluorine. So this is going to be dipole. Okay? All right, HCl. I have HCl, and chlorine is way more electronegative than hydrogen. Way. So, but it's not a fluorine, and it's not an oxygen, and it's not a nitrogen, so this is also going to be dipole-dipole. Okay, and then last but not least, I've got hydrogen fluoride. Also, fluorine's way more electronegative, and I have hydrogen bound to a fluorine, right? Fluorine, oxygen, or nitrogen. So this will actually be able to create H bonds, or hydrogen bonds, which is really, really strong. Okay, how did you guys do? All right, so draw each molecule and show the locations of hydrogen bonds between the molecules. Let's do 2 water molecules. So if I have water, remember, opposites attract. So the oxygen end is going to be partially negative, and the hydrogen end is going to be partially positive. So that means on another water molecule, the hydrogen is going to have to be attracted to the, you guessed it, oxygen. So if I have an oxygen of another molecule, it will be attracted through the hydrogen bond to the hydrogen of the other molecule. Okay? So opposites attract. How about ammonia molecules? So if I draw ammonia, and I'm going to draw it kind of sideways, that nitrogen end is going to be negative, and the hydrogen end is going to be positive. So if I draw another ammonia molecule, I'm going to have a hydrogen bond between the hydrogen on one molecule and the nitrogen on the other. Okay? How about a water molecule and an ammonia molecule? Do you want to try this on your own? See if you can make it work. You ready to check? Okay, there's 2 ways we can do this. We could have a water molecule. So if I draw a water molecule, if I have a negative end of the water, it could attract the hydrogen end of an ammonia, right? And I could have a hydrogen bond going that way. Or I could do the opposite. I could have the nitrogen on an ammonia being attracted to the hydrogen end of a water. Okay, both of those would work. All right, so that's how hydrogen bonding works. We have opposites attracting. The negative end is always going to attract the positive end. Okay, so now we're covalent. This is kind of a really fun area of intermolecular forces. We can have covalent bonds that form these big networks. For example, diamonds. Diamonds form this perfect tetrahedral network of carbons. And this is one of the reasons why diamonds are so strong. If I have a force on this one, it's going to just distribute that force through this whole molecule. So it distributes that force through the whole molecule and dissipates that force really, really easily. Okay? I could also have what's called a Buckminster fullerene ball. These were discovered at Ohio State, and that's why they're called Buckminster fullerene, because, Ohio State is the Buckeyes. And there was also an architect about the time that these were discovered that made geodesic domes whose name was Buckminster. So hence the double entrante there. And these are carbons kind of done with kind of soccer ball style. You'll see there's pentagons and trapezoids in here that create this round spherical thing. They are so slippery because they're totally nonpolar. They are used very often as lubricants in very high heat things because these can take much higher heats than oil. Okay? And then we'll have graphite. Graphite also is carbon that is bound in these hexagon rings. But notice it's in sheets. So we'll have a sheet and we'll have another sheet and another sheet. So in between these sheets, the only thing that is holding these sheets together are the London dispersion forces between those layers of the graphite. And the reason that we use graphite for writing is anytime we press down on the paper with our pencil, the force of pressing and dragging our pencil across that paper in the process of writing is enough force to disrupt the London dispersion forces between the sheets of graphite. So you're taking sheet off of the lead off a sheet to write whatever you're writing. Okay? So these sheets in and of themselves are really strong, but in between the layers, we only have London dispersion forces. Okay? These network covalent, glass is also a very good example of network covalent. We have silicon and oxygen that creates this really big network covalent layer. Okay, so let's talk about ordering these intermolecular forces from weakest to strongest. So these intermolecular forces, IMFs, we're going to go from weakest types of bond to the strongest. Okay, so the intermolecular forces, these are the forces in between molecules, right? So our weakest ones are just the ones that deal with electrons in non-polar situations, and those are London dispersion forces. So the absolute weakest are London dispersion forces, or LDFs. London dispersion forces are the weakest. Then next, a little bit stronger than that, are dipole-dipole. If I have permanent dipoles, those become pretty strong. Now remember, LDFs can become pretty strong the more electrons we have. So if I have really big molecules that have lots and lots of electrons, those LDFs can become pretty strong. Okay, but dipoles are not temporary. So they're stronger than the individual LDFs. Next are hydrogen bonding. Okay, hydrogen bonding are the next strongest intermolecular forces. And then next we have ionic. Now, ionic bonding, yes, is in between individual molecules, but if you've noticed, ionic bonds form these perfect crystalline shapes. We get this lattice, this crystal shape, and so there are molecules that go throughout this whole structure. They are our next strongest. They are really, really strong. And we'll see that because ionic bonded things have really super high boiling points and super high melting points. And then the next one, actually, I'd put metallic bonding in between here. Okay, metallics are not quite as strong as ionic bonding, the intermolecular forces between the metallic ions. And this doesn't want to let me write. And then the absolute strongest are our network covalent. Graphite, Buckminster fullerene balls, diamonds, anything that has this big network covalent bond is going to be super, super strong, even stronger than ionic bonds. Okay, so hopefully you had fun learning about IMFs, and next time we're going to start learning about phases between solids, liquid, gases, and we're going to learn how to read phase diagrams and learn about the energy that it takes to turn from one phase to another. All right, have a great day. We'll see you later. Bye.